The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
On Monday, when we went through and looked at the functional forms for sp2 hybrid orbitals as found in the case of the BH3 molecule. Now you should recognize that there are other hybridization schemes that go along with different geometries. So BH3 was trigonal planar. We're going to talk some more about BH3 today. If you had been considering last time instead a tetrahedral carbon atom, then the hybridization scheme we would have needed to develop would have been the sp3 hybridization scheme that would be associated with a tetrahedral carbon atom. On the other hand, if we had a linearly coordinated carbon atom or some other main group atom, boron or beryllium, for example, then we would have had to develop the sp hybridization scheme. So you should not miss the forest for the trees in putting into context my previous lecture on the sp2 specific case for that type of geometry. But now, rather than going through more examples of valence bond theory treatments of molecules, instead, it's time for me to introduce you to the tenets of the molecular orbital theory for treatment of molecular electronic structure. So I mentioned valence bond theory as having been introduced by Linus Pauling, and then I also named Robert S. Mulliken, MIT undergraduate, as the father of molecular orbital theory. And what these are both two different perspectives on viewing electronic structure of molecules that arises from the results of quantum mechanics. In the case of valence bond theory, we have a situation where you have localized electron pairs. In the case of molecular orbital theory, electron pairs are still going to be important, but they're going to be able to be delocalized over the entire molecule in some cases. So this is very different. This is a major difference between MO theory and valence bond theory. It is, in the case of the BH3 molecule that we considered last time, you had 4 positively charged nuclei, and you arrange those 4 plus charges at the points in space that correspond to the equilibrium geometry of the molecule. And then you sprinkle in your 6 valence electrons, and you want to understand how those 6 electrons become organized in space in response to that electric field set up by those 4 positively charged nuclei, right? And we took the approach last time that, okay, we were going to localize electron pairs in between nuclei, and because structurally the BH3 molecule is symmetric and the 3 hydrogens are indistinguishable from one another, we decided that we were going to make hybrids. And so we talk about hybridization. The idea behind hybridization was to change the atomic orbitals of boron by mixing them so that we would have one that would be able to point at each of the 3 hydrogens in space to form 3 nicely, perfectly directed 2-electron sigma bonds between boron and hydrogen. That was the scheme that we adopted, this hybridization scheme. But in MO theory, we're not going to do that. We're not going to interfere with the intrinsic atomic orbital structure of a boron atom in order to make bonds. And we're going to see that there are some predictions that come out of the MO treatment for the molecule that differ from those that came out of the valence bond treatment for the molecule. And so here are no hybrids. In terms of just the vernacular of chemical structure, you will hear sp3 as being used interchangeably with the notion of a tetrahedron. Okay? But in valence bond theory, it refers to a particular hybridization scheme in which we actually mix S and P as a preparative to bond formation in a molecule. And we mix the atomic orbitals on that central atom in a hybridization scheme. In MO theory, we're not going to do that. So it's very important that you keep these theories and the language associated with the series separate in your minds so you can see the difference between these theories. And then one of the consequences of this valence bond theory and the hybridization scheme is that it's not so good for excited states. And what that means is that we were developing a scheme to describe the bonding in the molecule in its ground electronic state. Molecules can have excited states just like atoms can have electronic states. And over here in molecular orbital theory, we're going to find that we do a much better job with excited states. And that's important for understanding the range of properties associated with molecular systems. Okay? And you're going to see indeed that the energy level scheme for the 6 valence electrons in the BH3 molecule is different depending on whether you use valence bond theory or molecular orbital theory. Now, for molecular orbital theory, we're going to need to have some kind of again, like we do for valence bond, we're going to need to have some kind of an idea of a procedure for forming molecular orbitals conceptually. Euler orbitals. And the first step in such a procedure is that you're going to want to analyze the three-dimensional shape of the molecule. And we do this, of course, when we talk about the valence shell electron pair repulsion theory for predicting molecular structure. So we're going to look at the structure, and we want to identify usually by inspection sets of symmetry related atoms or orbitals. And here I'm talking about atomic orbitals. So I'll come back in a moment and talk about what I mean by symmetry related. This is a concept that can be put on a very nice, firm mathematical footing. And in fact, if you find this type of analysis interesting and would like to see more of the math that can help you to organize the results of quantum mechanics in terms of symmetry, then you'll want to put the 504 subject on your calendar for the future. That subject is devoted in large part to the applications of group theory to chemistry and chemical problems. And symmetry plays a big role in that. And then 2, we're going to form combinations and let me just further qualify this by saying we're going to form linear combinations of symmetry-related orbitals. One of the big approximations that we usually kind of take for granted in the molecular orbital theory of electronic structure is the the LCAO approximation. So I'm just going to mention that parenthetically here. This is that we can form molecular orbitals that will be linear combinations of atomic orbitals. Okay, this approximation, this LCAO approximation, arises from the fact that we can solve the Schrödinger equation exactly for the hydrogen atom. But for big molecules and many electron systems, we can't. And so what we like to do is to take the atomic orbital wave functions, that's atomic orbital here in LCAO, and we like to use those wave functions in our approximation of molecular orbitals. So we're saying that we can combine these atomic orbitals on the atoms that are in a molecule to form the molecular orbitals that will be able to spread out and delocalize over the entire molecule. So this is inherent in the development of the theory that I'm working on here, and you should see that this will pop up in a number of cases, but it is an inherent approximation that we are accepting. And then 3, we're going to combine. We're going to combine the linear combinations from part 2 with central atom atomic orbitals. And that's what we will do. And when we've done that properly, we will have arrived at molecular orbitals for the system in question. So now I want to take a little bit of time to go through each one of these steps in order to define the problem that we have for this alternative way of viewing the electronic structure of the BH3 molecule. Now, why am I choosing the BH3 molecule for this? Well, I'm choosing it because it's an easy problem, and it's one that's illustrative of the steps that go into forming molecular orbitals for a system. In your textbook, you'll see that before you get to something like BH3, first diatomic molecules are considered. But those, I'll show you on Friday, are actually a little trickier to understand than is the case with BH3. And that's because in molecular orbital theory, we have the same number of MOs as AOs. Okay? So if we start out with a certain number of atomic orbitals that come into play by virtue of the atoms that are in the molecule, then that number of orbitals will be the same as the number of molecular orbitals that we will get at the end of the problem. Okay? They won't all be filled. We'll have some that are empty. Okay? But we're going to have the same number of molecular orbitals as atomic orbitals that go into the problem. And so what that means is that the complexity of the problem is related to the number of MOs and hence the number of AOs. The complexity of the problem scales with the number of atomic orbitals in the problem. We actually call these our basis functions. And one of the things that John Popel talks about, if you've gone and looked at his video that I pointed you to in the problem set, he talks about the wonderful fact that our computational power has gotten so great and will grow so much greater in the future that we're able to computationally handle problems of the calculations of the properties of enormous molecules that bring into a problem an enormous number, a vast number of atomic orbitals. And so great computational power is necessary to apply molecular orbital theory, or even the more recent density functional theory, to problems of electronic structure that we need to grapple with in order to predict properties of molecular systems. Okay? And in the BH3 molecule, which is, as I said, a simple problem of electronic structure, and a nice illustrative one for today's purposes. We have, this is a 7-orbital problem. Why is this a 7-orbital problem? It's a 7-orbital problem because boron has 4 valence orbitals, an s, a px, a py, a pz, and we have 3 hydrogens, each with their 1s orbital. Okay, so we have our valence orbitals on boron. We don't count the 1s orbital on boron because that's filled and it's a core orbital, and it doesn't get involved in chemical bonding. The valence shell for boron is the n equals 2 shell. We have 2s, 2px, 2py, and 2pz. And we have 3 hydrogens, each with their 1s orbital. So if we were to tackle right now the problem of the molecular orbital energy level diagram for a diatomic molecule like O2, dioxygen, we would find immediately that this analysis of how many atomic orbitals we have available would give us the value 8. And so it's a more complicated problem. It has 1 more atomic orbital than this problem, even though this one has 4 atoms, because 3 of these atoms happen to be hydrogens, which only bring in 1 orbital to the problem. Okay, so that's why I'm choosing this. And then in addition, I'm choosing this because the consequences of the symmetry of the BH3 molecule are that the orbital interactions that we're going to identify occur in nice pairwise sets. And that makes things especially easy to see in terms of how do chemical bonds arise in the context of MO theory for a problem like this. And so to now go ahead and carry out step 1 for this, we're going to draw the molecule and try to identify sets of symmetry-related atoms / orbitals. And before we do that, I just would like to show you an example of a highly symmetric molecule, because this notion of symmetry is something that at this point in time I really only want you to gain an intuitive grasp of. I'm not going to quantify it, but if you look at a molecule like the one I have, let's see, placed on the left and right hand screens, you'll see that it's a large round molecule. Actually, round things, spherical things, are the most symmetric things that we can think of. And here what we have, you can imagine that this is a big ball with atoms located at various points on the surface of the ball. This is just a ball and stick representation of the C60 molecule, also known as Buckminster fullerene. It's a geodesic dome type of molecule. And each carbon atom, so this molecule has the chemical formula C60. There are no hydrogens in this molecule. All the atoms are displayed, and each carbon atom sits in a position where it's adjacent to 1 5-membered ring and 2 6-membered rings on the surface of this spherical molecule. And that's true of every carbon atom on the surface of this whole molecule. As you go on in chemistry, if you go into the analysis of molecules using nuclear magnetic resonance spectroscopy, you'll find that it's really important to be able to identify the symmetry of a molecule, and you'll realize that the symmetry of the molecule is manifest in the nuclear magnetic resonance spectrum of a molecule. So if you take the carbon-13 nuclear magnetic resonance spectrum of this molecule, a sample composed of this molecule, you'll see that there is only a single C13 signal in the spectrum. And that's because all 60 carbon atoms are in an identical environment environment in this molecule. Every one of them feels exactly like everyone else. They're all equidistant from the center of this molecule. And they're all equidistant from their set of neighbors. And so in that way of looking at a molecule, you would see that they are all equivalent. Okay, so you may have encountered this molecule before, but this molecule itself, its discovery, it was actually predicted initially from analysis of mass spectrometry data by Professor Smalley, a Nobel Prize winner, whose efforts in this area have spawned off chemistries involving not only these nano-sized balls of matter, but also nanotubes made of carbon. And this whole area that we think of as nanotechnology, really a lot of it is dominated by the chemistry of new forms of carbon that arose with the discovery of Buckminster fullerene. And that is just one example of a new allotrope of carbon that was discovered in recent years. But this gives you an idea for symmetry. I could show you pictures actually of enormous biomolecules. You know, there are large viruses that are composed of biopolymers, macromolecules, that pack in a way that is symmetrical, so that you could see these things. If you view them in the right kind of representation, you'll be able to see the symmetry in them. And one definition of symmetry that I'd like you to take away from this picture is just that each of the atoms that are symmetry related are indistinguishable. If you turn the molecule around and you look at the atoms, those that are symmetry related are indistinguishable from one another. Okay? And so when we have a trigonal planar BH3 molecule, is the boron symmetry related to any of the other atoms? No, it's not. What about this hydrogen? I labeled them last time A, B, and C. This hydrogen labeled C, is it symmetry related to other hydrogens? Yes, and that's because of the symmetry of this molecule with these 120-degree bond angles and the planarity of the molecule. So you have a set of 3 hydrogens, and their 1s orbitals are in space indistinguishable from one another. So they're related by symmetry. And so in this problem here, we have 4 orbitals here on the boron that are not symmetry related. And then also, incidentally, let me point out that the boron atom is located at the center of gravity of this system. Okay? So if atoms are going to be symmetry related, they must not be located at the center of gravity of the system. Let's go over here and expand on these ideas. The method that I'm going to develop here for forming the linear combinations has to do with thinking ahead in this problem to the fact that we are going to want to make linear combinations that have the correct symmetry to bond to atomic orbitals on the central boron atom. Okay? So let me draw the ones that are going to be relevant to this part of the problem. This one over here would be the boron PZ orbital. So it's got one lobe coming, positive lobe coming out of the board, negative lobe going back. Over here we'd have the boron PY orbital using the coordinate system that I had chosen last time, which is X up and Y to the left. And then here we have the boron's PX orbital. And then over here we have the boron's 2s orbital. And so our challenge now will be to construct linear combinations, we're at part 2, of the set of 3 hydrogen 1s orbitals that can match in symmetry the boron central atom atomic orbitals. So last time, remember, for hybridization, we were making these orbitals mix with each other in order to point at the hydrogens. Now what we're doing is kind of an inverse concept. We're going to mix the hydrogen orbitals so that they have the right symmetry to interact with the central atom atomic orbitals. There's a nice parallelism here. So here's going to be our LCs. The key feature of the boron's 2s orbital is that it doesn't have any nodes. Remember, nodes are surfaces. When you pass from one side of a node to the other, you get a change in sign of the wave function. And we indicate that change in sign by differential shading. Okay? The 2s orbital has no nodes whatsoever. And a way that we can construct a linear combination that has the same spatial nodal properties as that boron 2s atomic orbital is as follows. We can involve contributions from each of the 3 hydrogen 1s orbitals. So remember, this one is A, this one is B, this one is C. This is going to be a linear combination of the 3 hydrogen 1s orbitals that will be, I'll write this one as follows. This one will be written as A plus B plus C. So that indicates the 1s orbital on A plus the 1s orbital on B plus the 1s orbital on C. And as we talked about last time, wave functions that we write should be normalized, and they should satisfy the unit orbital contribution rule. For normalization, here I give a factor of 1 over root 3 for this linear combination formed as a symmetry match with the boron 2s orbital. So you can see, I hope, how what we're doing is we're projecting the nodal properties of the central atom atomic orbitals onto the linear combinations that we're forming. And we're going to form a complete set of 3 linear combinations in this way. So let's make one that has symmetry properties that remind us of this px orbital. Okay? On HA, we're going to have a positive contribution to match the positive contribution of this lobe of the px orbital that points along the plus x axis. And then down here, we're going to have contributions from hydrogens B and C, and they're going to be smaller, and they're going to be opposite in phase. They're going to be opposite in phase because we're building a linear combination that has a node approximately at the center of the system here, so that as you go from positive x down into the negative x region of space, the wave function changes sign to match the change in sign associated with the px orbital. We're projecting the nodal properties of px onto the linear combination of hydrogen orbitals that we're forming here. And this one, written in normalized fashion, will be root 2 over 3 A minus 1/2 B minus 1/2 C. And although what we're working with here are linear combinations of these symmetry-related hydrogen 1s wave functions, you're going to find that these coefficients on the atomic orbitals that contribute to the eventually to the molecular orbitals are going to come out as normalized and as unit orbital contributions, so that if we started out this problem with a single 1s orbital on HA, that will be entirely accounted for among these linear combinations and the molecular orbitals that we're going to make with them. And then now let's generate a linear combination having the nodal properties of Py. And in order to do that, we need to have a negative coefficient out here in the minus y direction. So we're going to put in a contribution from HC as negative like that to match that. And then over here, we're going to make a contribution from HB that is positive, and then noting that there is a nodal plane along the YZ plane, which comes out of the board like this, so that we're always negative along minus y and we're positive along plus y. We match that here, and the coincidence of that nodal plane with the location of HA dictates no contribution from HA to this orbital for reasons that actually we looked at last time. Namely that we can't bring a hydrogen 1s orbital in here and also change sign on going halfway through that hydrogen 1s orbital, because s orbitals have to have the same sign everywhere. So it doesn't contribute to this linear combination. And our normalized form for this will be 1 over root 2 b minus c. And then if I were to ask the question, can I make a linear combination of the 3 hydrogen 1s orbitals that has the same nodal properties as pz, the answer would be no, because they all lie in the xy plane, and they're just s orbitals, and they can't change sign as you go through the xy plane from plus z to minus z. And so we're done here, and what you're going to find is that we've created these 3 linear combinations according to step 2, and taking into account both the symmetry properties of the molecule to identify a set of 3 symmetry-related atoms and orbitals, and then taking into account an analysis of the nodal properties of the central atom atomic orbitals so that we could project those out to help us find appropriate linear combinations for mixing with the central atom orbitals. And when we do that mixing, we're going to find out that there are 3 ways that we can do it. So we're about to move on to step 3 of this problem. We're going to need to combine these linear combinations with the central atom atomic orbitals according to the rules of MO theory to generate first bonding molecular orbitals, and the bonding molecular orbitals that we will get will be an in-phase combination of our LCs, our linear combinations of atomic orbitals, with our boron atomic orbitals. That will describe the chemical bonding in our system. And we'll see that it contrasts in a very interesting way with the hybridization scheme developed last time. And the key phrase to underline here is in phase. And what that in phase means is that when 2 positive lobes of 2 orbitals centered on 2 different atoms are juxtaposed and neighbor one another and can have good overlap of their atomic orbital wave functions, that leads to in-phase constructive interference and stabilization of the electrons associated with that newly formed bonding molecular orbital. And that stabilization is what we call the chemical bond. The analogy to that in valence bond theory is the idea that a pair of electrons associated with 2 nuclei in a sigma bond is more stable because it experiences simultaneously 2 positive charges. And here we're generalizing that and allowing electrons to flow over the molecule as a whole. But now we have a new concept, and that is anti-bonding. And anti-bonding molecular orbitals will be out-of-phase combinations that are repulsive and lead to high energy interactions. And when, as in the case of the problem we're considering here, the interactions occur in pairwise sets, we will find that we get very nicely for every bonding molecular orbital a corresponding anti-bonding molecular orbital. Okay. And also, one of the interesting things is that if you start putting electrons into anti-bonding orbitals, if your system just happens to be so constructed as to have many electrons such that you fill up not only the bonding molecular orbitals with electrons to make the chemical bonds, but you continue on and you have enough electrons to keep going and put them into anti-bonding orbitals, those antibonds start to cancel the bonds. And so you'll see a very nice progression of this as we study the MO theory of the homonuclear diatomic molecules starting on Friday. And then here's another concept that arises from the MO analysis of a molecule, and that is that certain orbitals can be non-bonding. And an example of this would be a lone pair of electrons, and it happens when an orbital or a linear combination of orbitals finds no counterpart of like nodal symmetry. These nodal properties of orbitals are very important. And I'll show you later how the nodal properties are related to the energies of the orbitals as we consider them. Okay, so having given you this preview of how orbitals are going to be able to combine in the MO theory, let's see how it actually takes place in the case of BH3. Now we're drawing another example of an energy level diagram where the energy is low at the bottom and it rises as it goes up. And these energy level diagrams that we are now developing for molecules are analogous to those that you studied earlier in the semester for atoms. And we're just generalizing this notion to the atoms. And what I'm drawing over here would be here's our boron 2s orbital, and here's our boron 2px, 2py, 2pz orbital. Those horizontal bars just represent the energy of these orbitals in the molecule. Here we have, I'm just redrawing the boron atom. And then now over here on the right, we're going to see that we have our linear combinations that we developed. These are our 3 H1s linear combinations. We found that the 3 hydrogens in BH3 were symmetry equivalent, so we generated linear combinations. The pictures of them are over there. I can give them names. Why don't I call them D, E, and F. So we have D. D was constructed to match the nodal properties of the boron's 2s orbital. E and F were respectively constructed to match the nodal properties of the boron's 2x, 2px, and 2py orbitals. And I'm showing you their relative energies. And now we need to do this issue referenced here as point 3. We need to combine these things. I've got these on the one hand and these on the other. Our 7 atomic orbitals have been changed into 4 atomic orbitals and 3 linear combinations. So I've still got 7 orbitals total. And now I'm going to combine these with these according to their nodal properties to generate 7 molecular orbitals. And let's do it this way. we're going to take linear combination D that has been constructed to match the boron 2s orbital in terms of symmetry properties, nodal symmetry properties, and we're going to make a bonding combination. I'm going to draw these in a moment. I'm going to draw these pictorially in a moment. And in this case, those are the only 2 orbitals in my 7-orbital system here that have that problem, have that set of nodal symmetry properties. And for every bonding MO, I must have an anti-bonding MO. So this is one of our molecular orbitals, and there's going to be a corresponding molecular orbital up here, high in energy, and this will be an anti-bonding molecular orbital. That will be the out-of-phase combination of the boron 2s with this linear combination that I labeled D. Anti-bonding molecular orbitals are usually denoted with a star. Okay? So we have a bonding combination and an anti-bonding combination. And then now we can form 2 more bonds that will spread out over the molecule, because if you recall, we had our px and py pair that served as the nodal template for our construction of linear combinations E and F. So we're going to be able to match up those to form 2 more bonding molecular orbitals. And these will be found to be higher in energy than the first one that we formed from D. So here's a bonding molecular, a pair of bonding molecular orbitals that derive from linear combinations E and F, combining in phase with borons px and py atomic orbitals. And there will be a corresponding anti-bonding combination where we allow those orbitals to interact in an out-of-phase manner. And you'll see what that means shortly. But let me put that up there and add a star to indicate that this high-energy pair of orbitals, molecular orbitals, is an anti-bonding pair of orbitals. I've got 6 orbitals now in my molecular orbital energy level diagram for BH3. And that means I'm not done, because I got to have 7, because I started out with 7 atomic orbitals. So look over here. 2pz was an orbital, an atomic orbital on boron that didn't find any way of serving as a template for making a linear combination involving the 3 hydrogens. And so it comes over here as non-bonding. Okay, it has no counterpart of like nodal symmetry because of the location of those 3 hydrogens in the xy plane, which is a nodal plane for the boron pz orbital. And so this one is non-bonding. These 3 orbitals up here are anti-bonding, and the ones down at the bottom, which are lowest in energy, corresponding to being able to most tightly hold on to electrons in them, are bonding molecular orbitals. And so our electrons can fill into this MO energy level diagram in that way. We have our 6 electrons that come into this problem. We have boron bringing in 3 valence electrons and 3 hydrogens each bringing in 1 valence electron. So there are 6 electrons to put into the diagram, filling up 3 of the molecular orbitals and then leaving empty pz. Let me introduce a little bit more MO language right now. This one here will be called the highest occupied molecular orbital, and this one here will be called the lowest unoccupied molecular orbital. And the reason why I'm drawing attention to these orbitals is that in chemistry, the chemical properties derive oftentimes from those orbitals that are in what's called the frontier orbital region. And the frontier orbitals are those close in energy to the HOMO-LUMO gap. And and I'll come back to this, but those highest energetically lying electrons are going to be the ones responsible for nucleophilic properties of the molecule and basic properties of the molecule and reducing properties of the molecule. Whereas low-lying empty orbitals are going to be the ones responsible for acidic properties of the molecule or oxidizing properties of the molecule. Okay, and we'll come back to that in a moment. But that is something pretty general and very useful that comes out of studying molecular orbital energy level diagrams. So now that we've got the diagram, let's see what the orbitals in the diagram look like. And I'll try to do this relatively quickly. Here, let's start with the lowest lying molecular orbital in the system. This is a representation of an in-phase combination of the boron 2s plus D, where D is defined up here as that linear combination. So this will be a molecular orbital that having the nodal properties of a 2s orbital centered on that central atom. And that's where our lowest lying 2 electrons reside. Now, if you look at the LUMO over there and then go up 1 orbital in energy, you will be looking at this orbital, which is the boron 2s orbital minus D. And the thing that makes this linear combination, this out-of-phase linear combination, so much higher in energy than its in-phase counterpart is the appearance now of a nodal surface. And this node is between the nuclei. It goes all the way around, and it is between the central atom s orbital and those peripheral hydrogens. And I'll show you a picture of it. So this is our BH3 LUMO plus 1 molecular orbital. Okay, so you can see that we have a wave function in the center of 1 sign, and then that as we go along any one of the BH bond vectors from boron to hydrogen, we change phase midway along the bond from positive to negative. And that's true no matter which of the 3 BH bonds we pick to traverse along. Okay, so that one has the nodal properties as drawn down there for the boron 2s interacting in an out-of-phase manner with linear combination number D, letter D. And so next time I'll finish up and show you what these other orbitals look like as calculated, but I hope you've enjoyed this. We'll see more MO theory on Friday.